Welcome to Compound Insights, a podcast by CFA Society New York. I'm your host, Rob Rowan. As AI evolves and financial services firms are adopting it, many CFA Society New York members find it natural to wonder what's next. Our podcast guest today knows. We're going to take this quantum computing topic on in a bit more elementary level than we usually do topics for this podcast. I believe that level is necessary as this topic is based far afield from ours, but the impact of it will be important as you plan your career. Now, I'm glad to say we have a very, very good guest today who knows more about this than basically anybody, but he is an engineer. Alberto Marchisio is a research group leader with the eBrain Lab, which is a division of engineering of New York University in Abu Dhabi. He works on hardware and software optimization and machine learning, brain-inspired computing, and other emerging tech. He has co-authored over 30 papers. Most of them were too engineering focused for me, but Google him, try, maybe you'll figure it out, listeners. Um, Alberto got his bachelor's and master's degrees in electrical engineering from Politecnico di Torino and his PhD in computer science from the Vienna University of Technology. So, Alberto, thanks for being on the podcast today.
Thank you very much, Rob. I'm glad to be here in the podcast.
So we are seeing an explosion of AI in the public sphere everywhere, right? It's being used to do everything from write Python code to make spaghetti. Stock markets are rising on it. People on the street are talking about it. But all of this makes the normal CFA Society New York member wonder how the booming demand for processing will be answered. So how do you think quantum computing will answer that boom?
Yeah, so it's a good question. So because we know that AI is shaping the world recently, so you can find AI everywhere and it can be applied to many application domains like for computer vision, robotics, healthcare, and for what is more interesting for the members of the CFA society, also the financial sector. And AI models require a large amount of data to perform well. So the AI models are becoming larger and larger every day. So just think about the latest large language models that have trillions of parameters. And on the other hand, the current computing infrastructures over the last decade has followed the Moore's law, where every 2 years, the number of transistors in an integrated circuit doubles. And also from the technological perspective, the transistor size is decreasing. So now there are concrete plans to develop like transistors that are going down to 1 nanometers, but is saturating at small sizes because it's approaching the atom level dimensions. So it's hard to continue scaling in this way. So this challenge offers us a very good opportunity to develop alternative technologies for different computing paradigms. And one of the possible solutions to solve this complexity issue is represented by quantum computing, because in classical systems, the set of bits that form the input signals are processed by classical gates, and the output signals is generated. However, for quantum computing, we start from a set of qubits that form a quantum state, and then the quantum gates perform the computation that alter the state of the qubits. And the measurement is conducted to capture the output.
Right. So this is, I think this is very interesting and also it just requires a little focus for a second. So if I understand it correctly, classical computer bits that run bits are either 0 or 1, open or closed, right? It's exceptionally simple. But qubits can be, if I understand it correctly, 0, 1, 0, 1, 0, 1 over here, 0, 1 over there. Like they're locational, they spin. Am I overstating that, or is that more or less what the deal is?
Yeah, you're right. Like we know the difference is that in classical system, there is a bit that can hold a value of 0 or 1, and in the fundamental unit of a quantum system is the qubits, that at each instance of time, the qubit can represent a mixture of state 0 and state 1. They following probabilistic distribution. And the final state is unknown and is determined by a measurement. And so there are some quantum physics phenomena that appear. So for example, the superposition principle says that a quantum system can exist in multiple states until its measurement. So until the measurement, qubit holds the state that is a superposition between 0 and 1. And when we measure, we obtain either 0 or 1 in a probabilistic manner. So if we run it multiple times, sometimes we get 0, sometimes we get 1. And of course, this concept can be extended when we consider 2 qubits or more. If we have 2 qubits, we have 4 states, 0, 0, 0, 1, 1, 0, and 1, 1, and so on.
Right.
And so that is, we can also explain to an example. So if we consider to have an object and we have every state that corresponds to a position of the object, and we can see that we can have position A, position B, position C, or D. And in classical system, we can sequentially check all the possible states of the solution. And we end up that, okay, 100% the object is in position, for example, B. And on the other hand, for quantum system, we have a different outcome because we know that the object is in position B, but we are only confident, let's say 60% about that.
This sounds like it's a massive increase over conventional computing. So how much bigger than Moore's law is it? Is it 100 times higher?
Yeah, it's not really 100 times. It's like increasing by exponential increasing. So if we have n features, we want to encode it with the classical system, we have to use n bits. But for quantum system, we can have a logarithm of n qubits. So that is a great increase.
This is one of the things that's a little bit difficult to wrap your arms around. So perhaps I would go with a sort of physical model for it. So the state of the data is as important as whether it's a 0, 1, a 0, 1, etc. That's where you get the logarithmic relationship.
Yeah, because the logarithmic relationship is like when you want to express combination of objects or combination of quantities in a system.
Right.
We can express this combination in a more compact form with using quantum computers.
Yeah. Okay. So the interesting thing about your work is, as I understand it now, is that some of these ideas and some of these processes are already existing on hardware that's out there in the ecosystem now. So can you talk about how people in the financial services area should look at companies like PennyLane or Qzit?
Yeah, so nowadays, like many companies are working on designing this quantum hardware and also tools and frameworks to implement QML algorithms on both the simulated environment and also the real quantum devices. And regarding what you mentioned, the Qiskit and PennyLane, there are very good tools to develop and designing quantum machine learning algorithms. So PennyLane is tool developed by Xanadu. It's an open source framework that is well documented and has a strong community. There are different application models like the interface for the dataset, the QML support, and applications like chemistry, auto differentiation, and interface with other languages. And there is also the very important access to Xanadu Cloud, where there are many tutorials and training materials for beginners and advanced users. So I encourage everyone to have a look at that. And also Qiskit, developed by IBM Quantum, is another very important framework for developing quantum systems. Is also open source, and there are a good quantum community to exchange ideas and support. There are different application models like Qiskit machine learning and optimizations runtimes. And there's also Qiskit has a set of tutorials for financial applications such as portfolio optimization, option pricing, and risk analysis.
Yeah, so I mean, this is excellent to know. I just would like to just share my experience with the members who are listening to this because I went on and did a little bit of stuff with PennyLane. I found it accessible. I also found it a bit like the experience I had when I first wrote my first script around NumPy in Python, because I thought my jaw hit the ground. I was like, oh, this is going to change everything. So if you like that experience, members, please go on to PennyLane because it will change the way you understand things completely. I guess there's one of the things that a lot of people will be listening to this for is an understanding of jobs. Now, there's a lot of job pressure in the financial services industry now in many, many different areas. So are there other on-ramps to this? And can you, as you are, obviously an engineer, but also familiar with the financial services industry, where do you think this is going to hit the financial services firms?
Yeah, it's very interesting to see because we are working on motivated by the fact that quantum computers are used to accelerate the predictions and speed up the execution of certain tasks. Mm-hmm. And for example, we see when dealing with large data, we want to have fast response and we want to consider many aspects. So I believe that this fits very well many of the financial problems, like, as I said, portfolio optimization, option pricing, and fraud detection, for example. So, and this can be accelerated in a very powerful way with quantum computers.
Yeah, well, this is, I mean, to me, this is absolutely fascinating, and I hope it has been for the members who are listening. So, first, let me say thank you, Alberto, for taking some of your time up to share your thoughts with the members.
Thank you very much, and thank you very much for an invitation as well.
And now, if you would like to see more about what Alberto thinks about this and his handout, which for our conference in January, which is excellent, and you're a member, you can see that recording on cfany.org. Just log in and you'll be able to see his presentation. It has a lot of other little places that you might want to go look at and research. But until next time, I'm Rob Rowan, and this has been Compound Insights.